Hello everyone, my name is Florian Aichinger from the Johannes Kepler University, and today I'm going to talk about Merton's portfolio problem for a multivariate Volterra model. This is a joint work with my supervisor, Sascha Demetre, also from the JKU. And to start, when we talk about volatility models, you might all be familiar with the famous Heston model. So in contrast to the Black-Scholes model, where the volatility is just a constant, in the Heston model, the volatility is a stochastic process itself. In particular, the volatility is modeled as a Cox-Ingersoll-Ross process, which is a mean reverting process with mean reversion level theta and mean reversion speed kappa. The parameter sigma can be interpreted as the volatility of the volatility. Additionally, in this model, we also allow correlation between the Brownian motions driving the return process and the volatility process with correlation rho. By a recent result of Garderal from 2018, we know that realized paths of volatilities are much rougher than the classical or established models would suggest. So therefore, the Heston model has been adapted to this rough case by using a convolution with a fractional integral kernel, which was done by Aichinger and Rosenbaum. Here the kernel has been chosen as t to the power of 1 minus alpha over the gamma function of alpha for a parameter alpha between 1/2 and 1. So basically, if alpha equals 1, we recover the classical Heston model. This fractional integral kernel is just a special case of a more general class of volatility models, the so-called Volterra-Heston models, which have been studied by Abi-Chabert. Here the volatility is again modeled as a convolution, but the kernel can be a more general L2 function. So far, all those models are only used for the monoacid case, which means we just have one stock to consider. But in order to get more realistic results, we want to have financial markets containing multiple assets. So we have to adapt the multivariate visual volatility model, which has been described in Boyle-Lee, to the Volterra model we have seen before. So the Volterra Wishart volatility model we use for our calculations looks the following. The volatility process is here matrix valued. So this is a variance-covariance process. Again, the kernel K is responsible for the roughness of our model. And the matrix M in the drift is determines the mean reversion. And the matrix Q is responsible for the volatility of the volatility. Again, as in the one-dimensional case, we allow the stock returns and the variance-covariance matrix to be correlated, which means that we can express the Brownian motion driving the asset returns as a combination, or in terms of the Brownian motion driving the stochastic volatility and another Brownian motion vector independent of both the other Brownian motions. The advantage of our Volterra Wishart model is now that we can capture many important stylist facts about real financial markets. For example, our investor can choose among multiple assets, as it is in real financial markets. We can also take into account the roughness of the volatility paths. Then we also have the correlation between the different stocks. And at last, we also have the so-called leverage effects, which means that we can model correlation between stocks and its own volatility. Our aim is now to investigate the so-called Merton portfolio optimization problem. Therefore, we have to consider so-called portfolio strategies. A portfolio strategy is just an RD-valued stochastic process where each of its components represents the proportion of wealth invested into the corresponding stock at a certain time. And for each such strategy pi, we consider the portfolio wealth process xt pi, which is just the value of our portfolio under the strategy pi at a specific time t. The aim of the portfolio, of the Merton portfolio optimization, is now to find a self-financing investment strategy which maximizes the expected utility from our terminal wealth. So in our studies, we assume that our investor has power utility function, which means that his utility can be described as 1 over gamma times x to the power of gamma. And we now want to find the value function depending on the initial wealth, such that the value function is the supremum over all admissible strategies pi of the conditional expected value of the utility of the terminal wealth. The strategy pi star for which this supremum is attained is then called the optimal strategy. And in this setting, it turns out that we can get explicit results for the optimal strategy and the value function. Namely, if psi is a local solution of the matrix Riccati-Volterra equation, depending on the parameters m, q, and v from the Volterra model, then on a time interval 0t, where t is less or equal than t max, an optimal investment strategy pi star for the Merton portfolio problem is given by 1 over 1 minus gamma times v plus a time-dependent term 2 times psi times q transpose times rho. And the value function can then be expressed as the initial wealth to the power of gamma over gamma times the exponential of such an integral. The idea of the proof is the following. We have to verify that the function g is indeed the value function and that our candidate for the optimal strategy pi star is indeed the optimal portfolio strategy. And to this end, it is sufficient to prove or to show the following 2 points. First, for the candidate pi star, we have to show that the conditional expectation of the utility of terminal wealth equals the function g for pi star, and for every other admissible strategy pi, we must have that the expectation of the utility of terminal wealth is less or equal than g. So finally, let's have a look at a numerical example to illustrate some of our results. Again, we have our Volterra Wishart model. And for our example, we consider a market consisting of two assets, namely the S&P 500 index and the 30-year US Treasury bond. And for those two assets, the Wishart model has been calibrated to real market data by Boraski et al. And therefore, for our model parameters, we obtain the following results for the mean reversion matrix M, the volatility matrix Q, the correlation rho, and the risk premium V. The roughness in our model, as we already mentioned, is obtained by using an appropriate integration kernel. For our purposes, we choose a fractional kernel, as we have already seen in the one-dimensional rough Heston model. Here, we use a diagonal matrix, and the diagonal entries we choose as the fractional kernels t over t to the power of alpha minus 1 over the gamma function of alpha. And again, like in the 1D case, alpha is between 1/2 and 1. So the investor we consider in our example his power utility function, and for his risk aversion parameter we choose gamma equals 0.2. So our investor is less risk averse than in the logarithmic case. So this is a kind of moderate risk aversion. And we are interested in the optimal strategy for this investor. So as you remember, the optimal strategy pi star consists of two terms, one constant term depending on the risk premium, and a time depending term, the so-called hedging demand, which is depending on the solution of the Riccati-Volterra equation psi, the volatility matrix Q, and the correlation rho, of course the parameter gamma. So in our example, we are going to simulate the hedging demand, and let's have a look at some results. Finally, let's have a look at the volatility and hedging demand for different roughness levels alpha. First, we start with alpha equals 0.95, which is very close to 1, the classical model. So you see that the paths of the volatility matrix are not very rough. On the right-hand side, we see the hedging demands, blue for the S&P 500 and orange for the Treasury bond. Both of the hedging demands are negative, which means that the investor is short selling stocks until both curves reach 0 in the end of our time horizon 1. For higher roughness, namely alpha equals 0.75, the paths, as we see, exhibit quite rough behavior. And compared to the first case, the curves of the hedging demands become flatter in the beginning of our time horizon and steeper when they reach the end of the time horizon, so towards 1. This trend is even more visible in the extremely rough case, alpha equals 0.55. Here the curves are very flat in the beginning, and in the end, they are turning to 0, quite steep. One note to the hedging demand. In contrast to the classical model treated in Boyle-Lee, we haven't been able to solve the Riccati-Volterra equation explicitly due to the convolution involved. So we had to use numerical methods to calculate the hedging demand and the optimal strategies. And this was all from me so far. Thank you for your attention.